So we're on question 3 on homework 13, and in my haste to attach screenshots onto the screen of the questions, I have a few issues with the words being missing at the bottom. So I'm just going to complete those, and I'm going to assume you guys can fill in the rest in your heads. So so it's saying that you have Bernoulli random variables 1 to n. You have a sequence of Bernoulli random variables and the parameter p, and with parameter p you have xi is equal to each and every Bernoulli random variable xi is equal to 1 with probability p, and xi is equal to 0 with probability 1 minus p. Right? What is the first question asking us to do? First question is asking us that given a sequence of actual values for the Bernoulli random variables, where each and every xi belongs to the set 0 or 1, that is, each and every xi can only take the small xi can only take a value 0 or 1. We need to find the probability of this sequence x1, x2 all the way to xn, and the sequence we're going to call f of x1, x2 all the way to xn. So what we're trying to find is f of x1, x2 all the way to xn. So whoops, small, let me erase that, because we want, it's a function of x1 to xn, so it's small x1, small x2 all the way to small xn is equal to probability that x1 is equal to x1 all the way to capital Xn is equal to xn. So our function is that the probability that each and every one of the random variables takes each and every one of the values mentioned. What is this equal to? Since each and every random variable is independent of each other, we can split this and say we can split this, erase off that stuff, and say x times, because they're independent, x2 is equal to x2 times probability of xn is equal to small xn. So now we see this, we've just broken this up in terms of the probabilities being independent, or the random variables being independent of each other. So we've split it up into nuclear probabilities of each and every xi equal to the respective small xi's. But can we do anything more with this? We know that x1 and x2 and such are just going to be 0 or 1. So can we split this up, or can we break this down into something smaller just using p and 1 minus p? Well, we can. So all you have to notice is that each time a capital X1 takes the value 1, then that particular term is going to be, or when capital Xi takes the value 1, that particular term is going to be p in this product right here. And whenever capital Xi takes a value 0, or rather small xi is going to be equal to 0, then that particular term is equal to 1 minus p. So the number of p's in this product is just going to be the number of 1's in the small xi's, and the number of 1 minus p's is just going to be the number of zeros. And since we're going to have n numbers, and we're going to have whichever numbers which are not 1 are going to be 0, because that's the only value xi's can take. Although those are the only two values xi's can take. So we have this is equal to p times p to the number of 1's in x1, xn times 1 minus p is number of zeros in x1 to xn. Let's say let number of 1's in x1 to xn equal no. Then what can you say about the number of zeros? Number of zeros, because everything which is not a 1 has to be 0, we're just going to have n minus no. So this is equal to probability of no p to the no, as in there are no ones, so we have to multiply p no times, and it's 1 minus p to the n minus no. So this is the answer for part 1. So function x1 to xn. Okay, so even though I've defined a function based on x1 to xn, and the answer does not have any x1 and xn in them, it's only because I'm defining no and no in terms of x1 to xn, or the number of ones in x1 to xn. So that's it for part 1, and let's just work on part 2. I'll just move all this I'll just move what I've written here up to the top so you can have an idea as we work on part 2. Alright, so we have part 1 over here. Now let's work on part 2. So now we have the random variable yn is equal to -1 over n log of f of x1 the way to xn. Observe that now the argument to the function is now the random variable itself and not the values the random variable takes. That's because the random variable yn is now a function of the random variables x1 to xn, and the value that random variable yn takes now depends on the values that x1 to xn take. So yn is a random variable which is a function of random variables and not the values which, well technically the values which random variables take. So, but it's a function of the random variable itself, and its value depends on the values which the random variables inside the function arguments take. So now let's actually work this out. We have 1 over n log of p to the no. I'm going to work with the same definitions as there, n minus no, which is equal to -1 over n, using the properties of logs, no log p plus n minus no log 1 minus p. So now this is equal to -no over n log p plus 1 minus no over n log 1 minus p. Now what happens as n becomes really large, n tends to infinity, yn is equal to negative. Let's not put the negative first, let's put the limit first. Limit n tends to infinity. Even though the limit obeys laws as if you have a limit of a constant times something, the constant can get pulled out. But I just wanted to write the entire expression. Log p plus 1 minus no over n log 1 minus p. So what can you say about this as n tends to infinity? What will no over n become? So we see that it's a binomial distribution of n zeros, because we have n IID random variables, and n zero is the number of heads or number of ones, and n is the total number of tosses. By law of large numbers, can you say anything about what n0 over n goes to? Well, n0 over n represents the fraction of ones as n tends to infinity. So what can you tell about the fraction of ones as n goes to infinity, as the number of samples goes to infinity? Well, the fraction of ones just goes to the actual true fraction, or it goes to the probability of getting one, or it's of getting one in any given IID random variable. So as n tends to infinity, the fraction of ones tends to the parameter of the probability of getting ones, which is just equal to p log p. Yeah, okay, so 1 minus p log 1 minus p. Just to reiterate that, so as n tends to infinity, in the fraction of ones which you have in your close to infinite samples of your Bernoulli random variable will go towards the true fraction which you're supposed to expect, which is just p. The true fraction, if you have n random variables, the expected fraction is going to be p. So as n tends to infinity, the fraction you observe will go towards the true expected fraction. So that's what we have. We have yn is equal to that. Therefore, this. So you might ask, okay, this is our answer. We're done with this. But you might ask, why is there a negative sign outside? Well, the point is that p and 1 minus p are numbers both between 0 and 1. So log of those numbers are going to be negative numbers. So if you want to get a positive value, or you want to get an estimate of what this is going to be, it might be a better idea to have a negative value on the outside. Now this function is actually yn is actually a very interesting function, or it's a very useful function. Limit n tends to infinity, let's say. Or it tells us something about our distribution. Yn over here in this case is actually called the binary entropy function, which is represented as h of p, which is p log p plus plus 1 minus p log 1 minus p. Well, it's called the binary entropy function if you're taking log base 2. So what does this represent? It represents basically how much randomness is there in your distribution. So why don't we actually plug in a few numbers to see how it looks? What if you plug in 0, right? H of 0 is going to be equal to negative 0 log 0, negative 1 log 1. Now 0 log 0 is defined to be 0, as in even though log 0 is infinite, 0 log 0 is defined to be 0, and 1 log 1 is defined to be, well, log 1 is 0. 1 is 0 is equal to 0. H of 1 is going to be again the same thing, except these two are reversed, right? You'll get negative 1 log 1, negative 0 log 0, which is again equal to 0, right? So we see that when we deterministically get 1 or 0, we have h of p, or h of 0 or h of 1 gives us 0. So it tells us that there's absolutely nothing random about our system. But if we have h of half, which is equal to half log to the base 2, negative half log to the base 2, 1 over 2, plus half log to the base 2, 1 over 2. So this is equal to negative log to the base 2, 1 over 2, which is equal to positive log to the base 2, 2, which is equal to 1. Right? So we see that it actually takes a maximum value at half. The graph of the entropy function looks like that, where at half this is p, and this is h of p. At half it's equal to 1, and at 1 and 0 it's going to be equal to 0. So this is how the entropy function looks. And it makes sense, because when you are when you get 1 half the time and 0 half the time, your system you can't make any prediction at all. You know that it's entirely random. So that the probability of getting a 0 or 1 is exactly the same. So you can get either 0 or 1 with exactly the same probability. So it's any sequence of random variables any sequence of values for the random variables is equally likely. So it makes sense that our entropy function takes a maximum value of 1 at this point. Yes, and that's about it for question 1 and 2. And we'll go on to 3, and we'll see that part 3 gives us the same value as the binary entropy function. Or rather, it gives us the binary entropy function even if we do that. And by that I mean whatever we have to do in question 3, which is we're gonna use Stirling's approximation to choose a fraction p out of n items, or you're going to take n choose np, where p is a fraction of ones which you're expecting to get, and we're going to see that it actually goes to the same thing.